Hey, AP Chem! Today we are going to be talking about how to find the empirical formula for a substance. And first of all, what an empirical formula is. It is, I would say, a continuation of our journey into chemical composition. We last looked at percent composition, and hopefully you guys are professionals at solving percent composition problems. And so we're going to kind of take that and extend that potentially to another scenario, which is an empirical formula. So what an empirical formula is a variation of a formula that we've been talking about already. The formulas that we've been talking about already for chemicals are what we call their molecular formula. So if you actually take a picture or take a look at a molecule and you see what atoms make it up and how many there are of each type of atom, that is what we call a molecular formula. Like if you took a snapshot of the molecule and counted up all the atoms in there, and then wrote the formula, that is the molecular formula, okay? It shows everything that's in there. That's how we find molar masses and all that stuff. What an empirical formula is it is the most reduced possible ratio of atoms in a molecule. So what it does is it takes the subscripts essentially in your compound and it reduces them to the lowest common whole, or not the lowest common whole numbers, but the lowest whole number ratio. So you have to reduce it down into numbers that are reduced, but also still whole numbers. So it's essentially the ratio of atoms that you have reduced down into the lowest possible whole number ratio. So for example, if we take a look at the compound here, B3H9, that would be its molecular formula. If I would want to figure out its empirical formula, I need to find a common factor between them and then pull that common factor out and reduce it down to get my empirical formula. And in this case, 3 would be my common factor between my subscripts, and I pull that out, and my empirical formula is BH3, okay? Another example would be water. Water is H2O, and if I look at them, I've got 2 and 1 for my subscripts. In this case, the lowest common factor that I can pull out is 1, and so my empirical formula is just the same as my molecular formula. So generally, what happens is when we talk about empirical formula, why we're using it is because we've run some sort of analysis on an unknown compound. Because you say to yourself, like, what good is it going to be for me to actually figure out just the ratio of elements in there? Well, if you are analyzing an unknown compound, what you can do is you can figure out how much of each individual element is in that compound, and then use a machine called a mass spectrometer to figure out how much your overall molecule weighs, and then you can actually figure out what your unknown is. And so that's kind of handy. So there are kind of 2 potentially different ways to solve empirical formula problems depending on how you get your data. You will see them in either problems where you are given masses of each of your elements that are in the compound, or you're going to be given percents, like a percent composition problem. So they'll be like, oh, it's 10% carbon and 35% oxygen or whatever. And so we're going to go through kind of how you solve those, and then through a couple example problems, and then give you a chance to do your homework. Okay, so you need to start your problem off with a starting mass. If the problem gives you the mass already, you roll and you just go with that problem. If it gives you a percentage, what you need to do is you need to assume you have 100-gram sample. And the reason why we do that is because if we have a compound that's 45% boron by mass, if you have 100-gram sample of that, it means that you'd have 45 grams of that sample. So what we're going to be doing is we're going to be either, like I said, if you get masses, start with the masses. If you get percentages, turn each element's percentage into a mass that matches its percentage, and then you commence with the problem. Okay. What you want to do is you want to find the moles of each element by using dimensional analysis. And in the case of diatomics, like our hydrogen, oxygen, fluorine, chlorine, bromine, iodine, nitrogen, you want to ignore the diatomicness of it. So when we're doing the analysis of it, it's going to be grams of H or grams of Cl, not H2 or Cl2. Because when we're talking about it in a chemical formula, it doesn't necessarily come in as a diatomic. It comes in just as however many of that particular element you need. So you're going to find the moles of each of them. Then what you're going to do is you are going to take the smallest number of moles that you get from your calculation, whatever that happens to be, and you're going to divide all of the moles by that number. And what that does is it says, well, this is going to be the number 1 in my compound. And what I mean by that is it's the subscript of 1. So for every one of this element, I'm going to have so many of the other element. When you get those answers are going to be your subscripts for your compound if you have whole numbers or close to whole numbers. If you have a half or a third or something like that, then what you need to do is you need to multiply all of the subscripts by that number. So for instance, if you get a half, like you get 2.5 for a subscript, you need to multiply all the subscripts by 2 so that you get a whole number. Do not round in the case of the subscripts. If you get a subscript that's like 1.33, that's a third. So you're going to multiply all the subscripts by 3 so that you get the whole number. Do not round down to get to 1. Okay. So we're going to do 2 examples. Oh, I lied. Gotta go back. So that's to find the empirical formula. Then if you know the molar mass of your substance, you can find the molecular formula. So what'll have to happen in that problem is they will have to tell you the molar mass of the big compound. And then what you need to do is find the molar mass of your empirical formula. So the reduced version of that formula. And then you are going to take the molar mass of the whole compound and divide it by the molar mass of the empirical formula. And what that does is it sets up a ratio. So if you have your molar mass of your big compound on top and then your empirical formula on the bottom in your denominator, if you get, let's say, a 3 for that answer, it means that your molecular formula is 3 times bigger than your empirical formula, and you are going to multiply that by 3. So everything in your subscripts get multiplied by a factor of 3. Okay, so now we're getting to the examples. So we're going to go through example number 1. I'm going to work through the problem with you in this video, and then you are going to try to do number 2, and we'll see how it goes. So example number 1 says, when oxygen reacts with phosphorus, 2 possible oxides can form. One contains 56.34% phosphorus and 43.66% oxygen. What is its empirical formula? And then the second part of the question is, its experimentally determined molar mass is 219.90 grams per mole. What is its molecular formula? So in an AP test situation, they would probably break this down into multiple parts. So they would be breaking it down like, oh, find the phosphorus, find the oxygen, then do the molecular formula. So what I want you to do is I want you to pause the video. I want you to attempt this problem using the rules that we talked about. So take your percentages, assume you have a 100-gram sample, convert to moles, divide by the smallest number of moles, all that jazz, and then figure it out. And then when you're ready, unpause the video, and then we will go over the answers. Okay, so let me get my camera up here for the problem, and then we will go over it. So in this particular problem, it starts off with percentages. So what that means is we're going to have, assuming that we have a 100-gram sample, and because of that, I would have 56.34% phosphorus, but because I'm assuming I have 100 grams, it's going to be grams of phosphorus. So 56.34 grams of phosphorus, okay? I'm also going to have 43.66 grams of oxygen there. So I've got both of those present in my sample in these particular quantities. And so what I need to do, first of all, is I need to do the conversion to moles. So if you forgot, we need to use our periodic table. And this is the table that you guys should have. And what I need to do is I need to use my molar mass on my periodic table. So here is phosphorus and here is oxygen. Now, I've told you that the oxygen and all your other diatomics, if you remember, your diatomics are nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and then hydrogen over here. In empirical formula, you are going to ignore those because we're talking about the amount of each atom in there, and it doesn't necessarily add as a diatomic in that case. Okay, so find the molar mass of phosphorus and oxygen, and we will use those. So in this situation, if I want to convert phosphorus grams to moles, I'm going to set up my dimensional analysis so that 1 mole of phosphorus is 30.97 grams of phosphorus. And then if you remember, I'll show you the work one time with this in my calculator. If I have a number on top, I'm going to multiply by that number. Number on the bottom, I'm going to divide by that number. So I am going to take 56.34, and then I'm going to divide that by 30.97. Okay, so I get in here, I feel like I got that good. Okay, so I have in here, it says 1.819 moles. Now it's not like super duper important that I round that perfectly, so I'm just going to put 1.82 moles of phosphorus in there. Okay, so I'm going to repeat the same thing for oxygen. 1 mole of oxygen is 16 grams of oxygen. And if I check my math just one more time to confirm, I'm going to get 2.73 moles of O. Now, one of the biggest mistakes I see people making is they say, oh, this is the ratio of the elements in the subscripts. No. What you have to do now is you find the smallest number and then you divide each of the numbers of moles by that smallest number. And the reason I do that is because in this case, 1.8 moles of phosphorus is going to be my smallest amount. What I'm saying is that for every 1 mole of phosphorus, I'll have so many moles of oxygen or whatever in my ratio. Okay, so what I'm going to get here is I'm going to get 1 mole of phosphorus for every 1 mole of phosphorus. Big shocker there. But if I take my 2.73 and I divide it by 1.82, I get 1.5 moles of O. So in this situation, I have for every 1 mole of phosphorus in my formula, I have 1.5 moles of O. So in theory, my empirical formula is PO 1.5, right? However, you know that I cannot have a decimal in my subscript, so I am not going to round this up to 2. What I'm going to do is take each of my subscripts and multiply them by 2, and I'm going to get an empirical formula of P2O3. So that is my empirical formula for this compound, for the first part. Now, the second part asked me to figure out what the molecular formula was going to be if it gave me my molar mass. So the molar mass that it gave me for my molecular formula, okay, that mass was 219.9 grams per mole. So that's the big boy. That's the big formula. We don't know what that formula is, but we know that formula is some variation of this. It's either the same or so many times bigger, like 1 or 2 times bigger, 3 times bigger, whatever. So what we want to do is set up a ratio where we figure out the ratio of this mass to how much this formula makes. So what I need to do is I need to figure out my empirical formula's mass. And so I'm going to do that by figuring out the mass of 2 phosphoruses and 3 oxygens. And when I add that up, I get 109.94 grams per mole. So what I have now is I'm going to do a ratio of the molecular formula's molar mass divided by the empirical formula's molar mass. And it's going to be 219.9, I believe it's 0, divided by 109.94. So when I do that, I get a number that is approximately 2. It's not going to necessarily be bang on perfect 2.00, but that's okay. And what this ratio tells me is that my molecular formula is twice as big as this empirical formula. So my molecular formula then is going to be P4O6 because it's twice as big. Okay, so that's what you're going to do if you have a percent given to you. Now let's go back to the presentation for just a second here, and we'll take a look at example 2. So here's example 2. It says a compound was analyzed and found to contain 13.5 grams of Ca, 10.8 grams of O, and 0.675 grams of hydrogen. What is the empirical formula? So this is different because it's giving you the mass already. It's not giving you the percentages. So what's nice here is that you can just take these masses and kind of run with them. So what I'd like you to do is, again, pause the video, work through the example and see if you can figure out the empirical formula. And then when you think you're ready, unpause the video, and then we'll go over the example. Okay, starting back up, we will get into our writing here and then see how it goes. All right, so this problem has 13.5 grams of calcium. It has 10.8 grams of oxygen and 0.675 grams of hydrogen. So again, you're starting with masses that are already given to you. You don't need to convert these into a percentage. I do see students sometimes who convert them to percentages and then to a 100-gram sample. And honestly, you're just doing more work. So if you're given the masses, just go straight to the moles. So I'm going to convert each of these to moles. And 1 mole of calcium weighs 40.08 grams. And if I do the math and figure out how many moles that is, I get 0.337 moles of calcium. For oxygen, 1 mole of O, again, not O2 here, is 16 grams. And so if I convert and do the math for the moles, I get 0.675 grams, nope, lies, moles of oxygen. Thanks for being patient with me. And then if I do the same thing for hydrogen, 1 mole of H, not H2, for 1.008 grams is equal to 0.67 moles of H. Now, when you do empirical formula problems, sometimes if you get good at these, you will recognize some ratios right away. So like these guys here are pretty much the same for their number of moles, which means that when I divide them by the same number of moles, I should get equal numbers for the moles of O ratio and H ratio. So since these are the same, when I divide by the smallest number, I'll get the same. You can also see here that this looks kind of like almost half of that. And so you'll kind of start to get used to seeing ratios with these. So I'm going to divide by the smallest numbers of moles. And so it's calcium the whole way through. So what happens is I'll have, for 1 calcium, I will have 2 moles of O and 2 moles of hydrogen. So when I write my empirical formula, I'm going to have Ca and then O2, H2. Now, in this case, the chemical formula is probably calcium hydroxide, which is CaOH2, because I don't know of anything where we're going to have O adding 2 and then separately adding 2 H's. It's probably going to be together as a polyatomic. However, on the actual test, they are not going to be fussy with the order you write them in. I usually write the element that there's one of first, but you don't have to. So it's kind of up to you. So the order isn't important. So you could write this as O2CaH2, and they're not going to mark it wrong. What tends to happen in a chemical formula, as you probably remember, is that the positive oxidation number gets written first. So in this case, the calcium is going to be a +2, so it'll get written as a +2. The same thing with phosphorus here. It's a positive in this case, so it's going to be the one written first. But again, they're not going to be super fussy about it. Okay, so hopefully these problems went well for you and the homework goes well for you as well. You're going to start to see with homework problems that past types of questions are going to get added in there, and that's to keep you in your memory fresh on those things. And when you take an understanding check, you're going to have to be kind of aware of that as well. Okay, so those old things might keep popping up because the test is incredibly integrated. So with that in mind, I just want to wish you good luck. If you have any questions, make sure you come to a meet and we'll talk about them then. Good luck.